scholars and families. Welcome back. I'm Mrs. DeVille and I was just getting ready to take out the recycling. But before I break down these boxes, I think we can use them for our lesson today. Let's see. Leave these here. And we are going to do a lesson today on perimeter, area, and volume. Before we get started, make sure you have a pencil and paper because as we did last week, we're going to write down our numbers and do some calculations. So I'll give you just a minute to get that paper and pencil in case you haven't yet. All right then, before we actually start taking some of our measurements, let's talk about what those words mean. Perimeter, area, and volume. Perimeter is the distance around a polygon. It is measured in units such as feet, yards, inches, or miles. And the formula for perimeter would be side plus side plus side plus side. Or perimeter equals length plus width plus width. Or perimeter equals 2 times the length plus 2 times the width. If all of that seems a little foreign to you, don't worry. We're going to talk about it through our lesson today. Area is defined as the measure of how much space covers a flat surface of a two-dimensional shape. The length and the width, 2 dimensions, length and width. It is measured in square units or units squared. And the formula for area is length times width, or area equals side times side. Volume is defined as the space that is taken up by a 3-dimensional shape, a shape that has length, width, and height. It is measured in cubic units or units cubed. And the formula for volume is length times width times height, or volume equals base times height. And again, when we get to looking at our boxes, we will have a better idea of what all those words mean. So in order to calculate the perimeter, area, and volume, we're going to need a tool. We're going to need a measurement tool. Now you may have a tape measure around your house. That would work very well. You might have, I found this tape measure in our garage. It's kind of cool. It clicks open. That's a pretty cool one. Or you might have just a traditional ruler. And if you picked up your enrichment kit, you should have a ruler in your kit. You probably have one around your house. If you're sitting there saying, I don't have anything, I can't measure anything, well, we have some everyday items that we can also use. So the length of an inch is approximately the distance from your knuckle to your other knuckle, I guess you would say. That's approximately an inch. So around my house, I found some dominoes that were about an inch. I have long fingers, so it's a little bit more. The bottom of the bubbles would be about an inch. The size of a quarter is pretty close. And there are other things you could probably find too. So just thinking about that fun fact that the distance on your finger, when it's kind of curled up, would be approximately an inch, and that could help you measure too. But for today, I have a ruler, so we're going to use our traditional ruler. And we need to set up our paper, our data table. So get your pencil ready, and you're going to write down what I'm writing down like we did last week. So we're going to make 4 columns. The first column is going to be labeled box, and that's just where we're going to identify the type of box that we're measuring. The second is that perimeter word that's spelled P-E-R-I-M-E-T-E-R. Perimeter. That's a very long word. The next word isn't so long, it's area. You can probably sound that one out. That is A-R-E-A. Area. And the last column, column number 4, is going to be for our volume. So volume is spelled V-O-L-U-M-E. So that's the 4 columns that we're going to need to record our data as we take our measurements. And we're going to figure out all of these things together. Earlier on the slides, you saw that there are some formulas for these. So let's go ahead and add the formulas. I'm going to switch colors here. And the formula for perimeter was side plus side plus side plus side was one way that it was presented, and the other was perimeter equals 2 times the length plus 2 times the width. And we'll go ahead and talk about those in just a minute. The formula for area, A equals L times W. A equals length times width. And our final one, volume, and this is especially important for our 5th graders. Volume equals length times width times height, or it may also be listed as base B times height. So again, as we go through our measurements, you'll be able to see what those mean. Okay, I think we're ready to start measuring. I've got my ruler. I'm gonna get my first box. My first box, you probably have one of these around your house, is going to be our rice box, and we're just going to take our measurements and record them. So I'm going to write rice box here, just so I can keep track of which one it is, and then we're going to do some measuring. Now, when we measure, we're going to measure these in inches, and we're actually going to do a little bit of estimation or rounding, just because we're not going to get into fraction or decimal amounts quite yet. We may do that at the end if we have time. So our length going across the bottom, I forgot, we're looking at our base first. We're not looking at the height yet, so we're looking at the base. The length of our base is 4 inches, and the height of our base is about 1 inch. So we're going to record those as 4 inches and 1 inches. So we're going to say that the perimeter equals 4 plus 1 plus 4 plus 1. Where did that come from? Well, again, on our base, which is the bottom, this is 4, this is 1, 4, and 1. So each side of our rectangle is accounted for. And when we add these, we can group them together if we want to. We have a property called the associative property, which allows us to do that. And then we know 4 plus 1 is 5, 4 plus 1 is 5, 5 plus 5 is 10 inches. So again, that is just the distance around. If we wrapped around this, we would need 10 inches of string or ribbon or whatever we might be using. So the area is the space to cover this entire surface, this entire flat surface. So for area, we're going to multiply length times width. The length was 4, the width was 1. So let's record it. Area equals length 4 times width 1. 4 times 1 is 4, and our units are now squared because it was inches times inches, so inches squared. Awesome. Now we're moving on to volume. Volume is the space inside. This is a 3-dimensional figure, so it's how much space is inside the box. So for this, we're going to use our length and width, which we've already calculated. Our length is 4 and our width is 2, but now we need our height. So let us measure our height. And the height of this box is approximately 7 inches. We're going to calculate it as 7 inches. So I'm going to list volume, V, equals 4 times 1 times 7. 4 times 1 equals 4. 4 times 7 equals 28. And this time, because it's volume, our units are cubed. So we represent that with inches, IN, and a small 3 to show that we multiplied 4 inches times 1 inch times 7 inches. So that's how we calculate perimeter area and volume using our rice box. Let's look for another box. This is a pretty blue box. And you notice anything different about this box compared to the rice box that we used? It looks different. This looks more like a cube. What would make this a cube? You're right. It has 6 sides and they are all a unique shape. They are all squares, or at least it looks that way. Now before we can go ahead and assume so, we want to measure and make sure. So let's use our ruler, and we are going to look at the base, the bottom, and we are going to measure the length, 4 inches, the width, 4 inches, and the height is also 4 inches. So each one of these is a congruent square. Each one of the faces is a congruent square. We have 6 congruent squares, all equal sides. So this one is going to be a little easier to record. We're going to call this one our cube because it has 6 congruent faces, and our perimeter for the bottom of our box was side plus side plus side plus side. The sides were each how long? 4 inches. So this is going to be 4 plus 4 plus 4 plus 4. I'll give you a minute to figure that out. Those of you that are quick, just did 4 times 4. 4 times 4 is 16. 16 inches. Great. Let's calculate the area. Area, we said, length and width are both still 4. So 4 times 4 equals 16. But now our units, because its area is inches squared, we multiplied inches times inches. And let's go ahead and calculate our volume. Our volume would now be 4 times 4 times 4. Each one of these sides is the same length. Length, width, height. Or base, 4 times 4 we found here is 16, and 16 times 4. 16 times 4. That's a little bit challenging. Well, 15 times 4, 15, 30, 60. So add on another 4, and that would be 64. 64 inches cubed. Okay, it's not that hard, is it? This is cool. All right. So we're going to look at 2 other boxes, and these are going to have some different characteristics. All right, so let's take a look at these 2 boxes. But rather than keep calling them boxes, let's get a little more technical. This is math class. These are rectangular prisms. Rectangular prisms. And they are rectangular prisms because they have 6 faces that are all rectangles. 6 faces that are all rectangles. So we have the top and bottom, the 2 sides, and the front and the back, and each one is in the shape of a rectangle. So we know that this is a rectangular prism. So when we record our information, let's use our more technical name. So the first one we're going to call the small rectangular prism, and when we get to the second one, we'll call that the large rectangular prism. So under box, I'm going to write small rectangular. I'll help you with the spelling. R-E-C-T-A-N-G-U-L-A-R, rectangular prism. P-R-I-S-M. Our small rectangular prism. We're going to calculate the perimeter, the area, and the volume. Now, in the interest of time, I went ahead and recorded these measurements for us. So in this box, the bottom, the base, the length is 4 and the width is 3. The length is 4 and the width is 3. So to find the distance around the entire figure, if this side is 4, then this side is 4. If this side is 3, then this side is 3. So we're going to record that as perimeter equals 4 plus 3 plus 4 plus 3. If I wanted to write 4 plus 4 plus 3 plus 3, is that okay? Absolutely, because we have a property called the commutative property that says that I can change the order of the numbers and not change the outcome. But we're going to keep it this way, and I'm going to go ahead and use that associative property and group those together because it makes it easier for me to add. 4 plus 3 I know is 7, and 4 plus 3 is another 7. 7 plus 7 equals 14. What are our units? Inches. Alright, now we're looking at the area, the space taken up by the base. So area equals length times width. Our length is 4, our width is 3. So we're going to record that as area equals 4 times 3. And I know that you know 4 times 3 equals 12. 4 times 3 equals 12. Our units are inches squared because it's area, inches times inches. 4 inches times 3 inches. That's 2 inches. So, volume. For volume, we need one more measurement. We need the height. The height of this rectangular prism is 2. So we're going to do length times width times height. Volume equals 4 times 3 times 2. 4 times 3 we already said equals 12, and 12 times 2, or 12 plus 12, is 24. And our units are inches cubed. So the volume of this box, the space inside, is 24 inches cubed. Now let's look at the large rectangular prism. So for our large rectangular prism, let's go ahead and record that on our chart. Large rectangular, R-E-C-T-A-N-G-U-L-A-R. Prism, P-R-I-S-M. Our large rectangular prism, our bigger box. So again, I've already measured these out for us. This one has a length of 8 and a height of 9. So the base here has a length of 8 and a height, a width of 9. I said height, that's not right, it's width. 8 and 9, length and width. So we know that the perimeter, the distance around, is going to be, that's wrong. Stop it. That's not 9, it's 6. Alright, now we're going to look at our larger rectangular prism. So again, I have already marked our measurements for us in the interest of time, but let's go ahead and label our chart. And I'm just going to shortcut it and call this LRP, large rectangular prism. You can write the whole thing out, but I want to make sure we get everything done today that we need to, so we're going to keep it moving. So perimeter, our length is 8, our width is 6. Length is 8, width is 6. So again, if this is 8, the top side is 8. If the right is 6, the left is 6. So we're going to record our perimeter as 8 plus 6 plus 8 plus 6. And if we group those together, 8 plus 6 is 14. 14 plus 14, 28 inches. So the distance around this rectangle is 28 inches. Area. Area equals length times width. Length is 8, width is 6. We're getting the hang of this. Area equals 8 times 6. 8 times 6, 6 and 8 went on a date. They came back with 48. 8 times 6 is 48. Our units, inches squared. Put that little 2 up there. And the volume of this box. So we have a length of 8, a width of 6, and a height of 4. Our height is 4. So let's go ahead and record. Our length is 8. Our width is 6. And our height is 4. And so we're going to multiply 8 times 6 is 48, and 48 times 4. 48 times 4, well, that's a bit of a challenging one, but we could do 50 times 4. 50 times 4 is 200. Take away 2 groups of 4, that's 8. That brings us down to 192. 192. And I know we did that kind of quickly. You can write that down later to make sure that I'm right. 192. So remember I said we're going to look for some interesting connections between these two rectangular prisms. So if we are looking at them, and I'm going to go ahead and just do a little rough sketch here of our rectangular prisms. So we had the smaller one, and then we had the larger one, and obviously these are not drawn to scale because these are not exactly the same size, but just to give you an idea here. And let's record those measurements that we had. So on the small rectangular prism, we had a length of 4, a width of 3, and a height of 2. With our larger rectangular prism, we had a length of 8, a width of 6, and a height of 4. Now I want you to take just a minute and look at the comparison between those numbers and tell me if you notice anything. So hopefully you notice that each of these sides was doubled. So the 4 doubled to 8, the 3 doubled to 6, and the 2 doubled to 4. Now my question is, if we double the sides, what happens to the perimeter, the area, and the volume? Well, let's take a look at that. So when we double the sides, small to large, our perimeter went from 14 to 28. 14 to 28. Is there a relationship between 14 and 28? 28 is twice as much as 14. So when we doubled the sides, our perimeter doubled. Let's see if I can record a little bit of this. So when we double the sides, the length of the sides, our perimeter doubled. And what does doubled mean again? It means it's 2 times as large. So 14 times 2 equals 28. Interesting. I wonder if there's a relationship for our areas. Our original area was 12, and when we doubled the sides, the area turned 48. Is there a relationship between 12 and 48 that we can see? 48 is 4 times as large as 12. 12 times 4 equals 48. So our area quadrupled. Quadrupled means times 4. 4 times as large. Wow, that's interesting. And what about the volume? What happens with the volume? The volume went from 24 to 192. Well, I'm going to help you out here because that's not a real easy one to do mentally and quickly. 24 times 8 equals 192. 24 times 8. So this is 8 times as large. I wonder why that is. Well, if this is 2 times longer, and this is 2 times longer, and this is 2 times longer, 2 times 2 equals 4, times 2 equals 8. That's why this is 8 times larger. What does that mean? That means that 8 of these little boxes could fit inside the larger box. And you can kind of picture that if you look at 1, 2, and then you would have 2 on the other side, 3, 4, and then have a second layer of 1, 2, 3, 4. Now again, this doesn't work exactly because we did a little bit of fudging with our numbers just to make them nice even numbers, but that is pretty cool. That's what has happened here. So lots of things that we can do with our measurement with our numbers. If you remember at the beginning, I said that we were going to estimate, but you can also be more, especially if you're a 5th grader, you can be more precise and bring in your fractional sides. And if we had more time, we would do that. You can also use your figures around the house to measure, and your dominoes. I brought out the dominoes. They line up real nicely. We said this had a side of 4. It's kind of hard to show you here, but you can see possibly that we can line up the 4 dominoes for 4 inches, and that works perfectly. So spend some time around your house, find some things that you can measure, look for the perimeter area and volume, and if you don't remember, you can replay the show and find out how to calculate measurements around your house. I hope that you have enjoyed today's lesson, and I hope to see you again next week. I'm going to now throw it over to my partner, Miss Siegler.
So you're walking along and you come across a sidewalk that looks something like this. Have you ever seen this in your neighborhood, where a tree seems to have grown up under it and split it apart? Have you ever gone on a hike and come across a creek that looks something like this? Have you ever wondered where all these rocks come from? How do all these tiny rocks get into this river? What about these big cliffs? How did that happen? Did a meteor strike and carve out this giant area? Where did it come from? Today I'm in Mill Hollow in Lorain County, which is a metro park. We're gonna look around and explore a little bit and see if we can find some examples of weathering and erosion. Weathering and erosion are 2 important processes that affect the physical world around us. If you like going to the beach, or if you hate driving over potholes, weathering and erosion is something that you've experienced and have firsthand knowledge of. Weathering is the breaking down of rocks on Earth's surface into smaller and smaller pieces. And this is easy to see. Here you can see this gigantic rock, and all across it there's pits and scrapes, big cracks. It has a very rough exterior, and this has happened at least in part from weathering. Weathering can break down the Earth's surface through wind, water, ice, or plants. Here we can see that the river is moving pretty fast. And if we were to look at it closely, we would see that some small rocks are being carried along by it and are crashing into other rocks, breaking chunks off and causing weathering. Eventually, weathering creates sediment, which is sand, rocks, fossils, and other matter carried and deposited by water, wind, or ice. Here you can see the sediments that have settled alongside this river, including sand, little bits of rock, and more. Root wedging is another form of weathering where roots grow into cracks in rocks and split them apart over time. So if you see these crazy roots, if these were to grow into rocks nearby, like boulders, they could split them slowly, expanding the cracks in the rocks as the roots grow. I thought I saw a fish over here. Gonna stick this in the water, see if we can see anything. And just mud. Leaves and mud. And air bubbles. Another kind of weathering that I can't show you in the wild right now, but that you see every single winter here in Ohio, is ice wedging, which is a form of weathering where water seeps into cracks in rocks and splits them apart when the water freezes, a lot like root wedging. This is what creates potholes here in Ohio. The water seeps into cracks in the asphalt, especially in the winter, and when it freezes as the temperatures go down, the water expands and makes what would have been a small crack into a much larger crack. Now, I don't know what kind of weathering or crazy thing caused this, but here's an example of how powerful the simple processes can be. Look at this hole in this rock. When rocks are broken apart by weathering, they are then usually carried away, and this is through a process called erosion, which is the process of moving the weathered rock and sediment from one place to another. And so a good way to remember this is that weathering breaks the rocks apart, but erosion carries them away. A good example of this is a river. Here you see the river, and if you look over the edge, there's almost a little cliff here, and the soil and sediment have been eroded away, leaving this enormous gap. So the river has come in, swept away the soil, the sediment, small rocks, and deposited them somewhere else. Now, if you think about it, erosion could be a major problem. Like, what if your house was right here beside this river? Would your house be very safe if the river was eroding the soil underneath it? I wanted to get under the water so you could see the sediment being moved through erosion. But as you can see, it's pretty clear today. There's not a lot of sediment in the water, though if you look closely, and I've slowed it down a lot, you can see little bits and pieces in the river. Now, if there had been a big rainstorm or the water was moving more swiftly, the water would have more power and be able to move larger rocks and larger pieces of sediment, and the water would also be a lot murkier. Erosion can be pretty powerful. This river could get flooded and wash away boulders, houses, pretty much anything including people. So you always want to be careful when you're exploring near a creek or a river or any kind of body of water. It's very easy to trip, and the force of the water can actually push you and hold you under the water. So always be careful when you're exploring near bodies of water. If you're the kind of person who wonders about these rocks, these are called shale, and specifically Ohio shale. This shale formed over 375 million years ago. This kind of rock is great for finding fossils. Here's a pretty huge rock that I found, and it's crazy to think that erosion could have moved it just using the power of the water. You've probably seen areas like this around your city, and in this ditch you can see very clearly how erosion has swept away the soil and the sediments from the top. We humans often dig ditches like this on purpose to direct the water so that erosion doesn't happen where we don't want it to, like underneath our homes. So after a rock has been weathered and broken apart, and then erosion has carried it somewhere new, after all that has happened, deposition can occur. And deposition is the dropping or settling of eroded material. And you see this all the time. Lake Erie is a perfect example. When you go to the beach surrounding Lake Erie, oftentimes you find huge pieces of wood, strange rocks, even pieces of trash that have been dropped onto the beach by the waves. Here you can see a ton of sediment, little fossils, little rocks, soil, sand that have been dropped and deposited at the side of this river. Oftentimes deposition occurs when the water no longer has enough force or power to keep moving the sediment. So the sediment is heavy and the water doesn't have enough power, so it just kind of lets it drop. As I continue walking, you can see that there's even giant boulders all the way up here, way far away from the river. And that could be because they were deposited. Maybe there was a larger flood and the water had enough power to move these boulders up here. So now we know how these cliffs here most likely occurred. It probably wasn't an asteroid, but just the slow process of weathering, erosion, and deposition. Ice probably forms in the cracks in the rocks every winter, and I'm sure gravity helps pull those rocks down to Earth. If you look closely on the cliffs, you can even see that there is plant life growing up there, including even trees, and that's helping weathering along as the roots grow into the cracks in the rocks, causing root wedging. And when weathering has broken down all those rocks, you can see there's giant piles sitting right at the edge of the river. The river can easily carry those sediments away now. Over time, eventually this river will be even wider than this, because it will have eroded and weathered away the whole cliff. The best part about erosion, weathering, and deposition is that it's an easy enough thing to model at home using a stream table. A stream table is a way to model and experiment with erosion at home. It's pretty fun and pretty easy, but you'll want to make sure you have your parents' permission and probably do it outside. To make a stream table, you won't need much. All you need is soil or sand, water, and a flat pan. You might also want some rocks because it's fun to see how erosion can carry them away, even in this small model. You'll also want something to prop your table up at an angle so the water will flow down towards the bottom. So here's my setup, and as you can see, I've tilted it up and I'm gonna stick rocks all over the top of it. You can also see that I got the sand moist first, and that's so the loose sand doesn't just fall everywhere. You want it to be in a nice little pile. If you have a smaller pan, it's a lot better too. You want nice sides, you fill it all up. Now, when I start the water, you'll notice almost immediately that a little river starts forming. And very quickly, you see the erosion begin to happen. If you notice at the bottom, you can also see where the rocks are being deposited. Now, I'm using a lot of water, so it's going pretty swiftly. If you want to make it look a little bit cooler, you can go pretty slow and use just a little bit of water, a thin stream. If you want your river to go a certain way, you can also try moving the sand or shaping the sand so the river goes through maybe a small ditch. There's a lot of different things you can do with this kind of model. One thing I like to do is to model how glaciers work. And to do that, you can take some ice cubes and put them on your stream table. And some interesting things happen when you do that. You can also try different mixtures of soil, sand, sediments, rocks, basically anything to see how erosion is affected by different materials that the water goes through. There's basically no limit to how creative you can be with this kind of model. A few fun challenges you can try is, can you prevent the erosion from happening? Could you build something or add something to the stream table that would prevent the erosion? You can also try forming different landforms out of your soil or your sand and seeing how the erosion is affected when the water runs across mountains or things like that. Just create something cool and discover something new.
Today, we will take a hike, learn a few poetry elements, use adjectives, and write a haiku. What is a poem? Have you ever wondered what a poem actually is? Is a Taylor Swift song a poem? Is your favorite rap a poem? Yes! A poem is a type of writing that uses lines, rhythm, figurative language, and other elements to communicate emotions and ideas. Poetry doesn't have to rhyme and doesn't have to be punctuated like sentences and paragraphs in other kinds of writing. Poetry requires creativity and the use of figurative language. Remember similes and metaphors? Adjectives can help us when we're writing poetry. Adjectives are describing words. Examples include smelly, green, wonderful, tired. Adjectives are a good choice in poems because they help to get your feelings across to your reader. Today's poem is a haiku. A haiku is a Japanese form of poetry. It has 5 syllables in the first line, 7 syllables in the second line, and 5 syllables in the last line. A lot of times haikus are about nature. In today's poem, the haiku, here's an example. In the first line, it has 5 syllables. 5 lovely geese fly. The second line has 7 syllables. Across the lake and green grass. And then again, 5 syllables at the end. Where are they going? Got it.
Got 1 second.
If you
I'll cut this out. Keep going.
If you're having trouble understanding how to put the right amount of syllables, think back to when we sound out words and we clap the number of syllables. You can do that for each number. 5 for the first line, 7 for the second line, and 5 for the last line. As we go on our virtual hike, use what you see to inspire your writing.
Let's go back to that little place where we used to go in the summer days. We dip our feet at the water's edge, and everyone would come along to meet us there. We'll have a competition to see who can trap for longer, 'cause every year my body's getting stronger. We can swim all day and dance until the night.
Hello everyone, my name's Jason Levy and I'm the music teacher from Campus International School. One of my favorite things to do is to travel all over the world. So hopefully your bags are packed and you're ready to join me for our musical journey today. Our song Oeana comes from the Polynesian Islands, which are located in the southern part of the Pacific Ocean. While there are many Polynesian islands, this particular song is believed to come from the Cook Islands, just to the west of Tahiti. These are lush, tropical islands with beautiful blue waters, spectacular views of mountains, rainforests, and volcanoes. The Cook Islands consist of 15 different islands, some of which are over 100 miles apart from each other. The song Oeana is in a style called a kaparima, or an action dance. This is where there are hand gestures that go with the words to the music. So as I'm doing them, see if you can figure out what some of these gestures mean and how they relate to the music. So while I'm doing them, please do them with me and mirror me. So let's start Oeana. Excellent job with your kaparima style dance. So hopefully while you were doing it, you were able to recognize what some of these motions were. So you could see the waves that were coming up maybe over the boat, and those waves were making the boat rock some. And then sometimes in the water, there are these whirlpools that swirl us around. And when the Polynesian islanders were going from island to island, they would look over the horizon and they would go in all directions to try to find land. And then the music suddenly got faster. And who knows, maybe there was a shark in the water, so they had to paddle really, really fast. And they would go through the day and through the night. So they had to eat stars. And then sometimes they'd just be so tired and so hot that they'd dive into the water. So again, please try again our dance of Oeana in the kaparima style. That was wonderful. Thanks so much for joining me on our adventure today in the Cook Islands with Oeana. Again, I'm Jason Levy from Campus International, and I hope to see you next time on our next journey. Thanks!